On October 26, 1707, four warships of the Royal Navy smashed into rocks off the Scilly Isles and sank within minutes, taking over 400 sailors to the bottom of the sea, including Admiral Sir Cloudesley Shovel, one of Britain's most experienced naval commanders. The fleet had been sailing home from Gibraltar, navigating by dead reckoning through days of storms and overcast skies. The admiral consulted with his navigators, and they assured him the ships were off the coast of France. They were wrong by over 100 miles. The disaster shocked the nation and exposed a terrifying truth. The Royal Navy, the most powerful maritime force in the world, could not reliably determine its position at sea. Ships navigated by guesswork, and when the guess was wrong, sailors died. The problem was longitude. Latitude, the distance north or south of the equator, could be measured by observing the sun's height at noon or the angle of the North Star at night. But longitude, the distance east or west of a reference point, required knowing the exact time. The Earth rotates 15 degrees of longitude every hour, so a clock error of just 4 minutes translated to a navigational error of 1 degree, roughly 60 nautical miles. On a long voyage, such errors compounded, leaving ships hopelessly lost. Captains knew their latitude, but had no idea how far east or west they had traveled. The result was disaster after disaster. Ships ran aground on invisible reefs, missed their destinations by hundreds of miles, or wandered aimlessly until supplies ran out. In 1714, the British Parliament passed the Longitude Act, offering a prize of £20,000, a fortune equivalent to millions today, to anyone who could solve the problem. The prize would be awarded to a method that could determine longitude at sea to within half a degree, or about 30 nautical miles. The best astronomers, mathematicians, and scientists in Europe competed for the prize. Most believed the solution lay in astronomy, in precise observations of the moon's position relative to stars, a method called lunar distances. Sir Isaac Newton himself had declared that, while a clock might keep time for a few days, it could never maintain accuracy over the weeks or months of a long voyage. A carpenter from Yorkshire was about to prove him wrong. John Harrison was born on March 24, 1693, in Falby, a small village in West Yorkshire. His father was a carpenter who also served as the estate carpenter for Sir Rowland Wynne at Nostell Priory. John followed his father into the trade, learning to work wood with precision and to understand the behavior of materials under stress. He had little formal education, but he taught himself mathematics, mechanics, and the principles of timekeeping by reading books borrowed from local scholars. By his early 20s, Harrison was building clocks as a sideline, using wood instead of metal to avoid the friction and wear that plagued brass movements. His clocks were astonishingly accurate, losing only a second per month, far better than any commercially available timepiece. Harrison's breakthrough came from understanding friction. Traditional clocks used metal-on-metal bearings that wore down quickly, required constant lubrication, and introduced errors as the oil thickened in cold weather or thinned in heat. Harrison invented the grasshopper escapement, a mechanism where wooden arms moved in a way that minimized friction and required no lubrication. The arms kicked like a grasshopper's legs, hence the name, transferring energy to the pendulum with minimal loss. He also developed temperature compensation using strips of different metals that expanded at different rates, automatically adjusting the clock's rate as temperature changed. These innovations made his clocks reliable and accurate, and they caught the attention of London's scientific establishment. In 1730, Harrison traveled to London with drawings for a marine timekeeper designed to solve the longitude problem. He met with George Graham, London's leading clockmaker and a fellow of the Royal Society, expecting skepticism. Instead, Graham listened for hours, examined the drawings, and lent Harrison money to build his design. Graham recognized that Harrison's approach, using mechanical compensation and friction-reducing mechanisms, could succeed where others had failed. With Graham's support, Harrison began work on his first sea clock, later known as H1. He spent 5 years building it, solving problem after problem, testing every component, and refining the design until it met his exacting standards. H1 was completed in 1735. It was a large brass mechanism weighing 72 pounds, with two dumbbell-shaped balances connected by springs to compensate for a ship's motion. Instead of a pendulum, which would swing wildly on a rolling deck, H1 used the linked balances to maintain steady timekeeping. Harrison incorporated his grasshopper escapement to minimize friction, and he used bimetallic temperature compensation to counteract thermal expansion. In 1736, H1 was tested on a voyage to Lisbon and back. The clock performed well, even alerting the captain when the ship's navigation was off course on the return journey. The Board of Longitude, impressed but cautious, granted Harrison funding to build an improved version. Harrison built H2 by 1741, incorporating refinements to eliminate weaknesses he had identified in H1. But before H2 could be tested at sea, Harrison discovered a fundamental flaw. The balance system was vulnerable to certain types of ship motion that could disrupt its accuracy. Rather than test a flawed design, Harrison abandoned H2 and began work on H3, determined to solve the problem definitively. H3 consumed 19 years of his life, from 1740 to 1759, as he pursued perfection. He invented the bimetallic strip for temperature compensation, a device still used in thermostats today. He developed cage roller bearings to reduce friction, an innovation that became standard in mechanical engineering. H3 was a masterpiece of ingenuity, but it never quite achieved the precision Harrison sought. During his work on H3, Harrison had a revelation. In 1753, he commissioned John Jeffreys, a skilled London watchmaker, to build a precision pocket watch to his specifications. The watch was unusually accurate, thanks to Harrison's novel balance design and other improvements. Its success made Harrison realize that smaller might be better. The solution to the longitude problem might lie not in ever larger clocks, but in a finely crafted watch. Harrison made the bold decision to set aside H3 and begin work on a radically different fourth timekeeper, a watch-sized instrument that would become H4, the device that would ultimately win the longitude prize. Work on H4 began in 1755 with Harrison now in his early 60s. He poured all his hard-earned lessons into this device. By 1759, Harrison, assisted by his son William, completed H4, a gleaming, exquisitely detailed watch about 5 inches in diameter, enclosed in a double silver case. At first glance, it looked like an oversized pocket watch. Inside, however, it was a masterpiece of precision engineering unlike anything before it. Harrison had essentially created the world's first marine chronometer, a portable clock capable of keeping nearly constant time over long sea voyages. H4 featured a fast oscillating balance wheel that ticked 5 times per second, making it less prone to disruptions from a ship's swaying. Harrison tackled the two biggest enemies of accuracy: temperature changes and uneven driving force. He equipped H4 with a temperature-compensated balance spring that adjusted automatically as conditions changed, and he added a mechanism called a remontoir to equalize the mainspring's force, ensuring that the watch ran at a constant rate, whether the spring was fully wound or nearly exhausted. He also incorporated maintaining power, a device that kept the watch running while it was being wound, preventing the loss of time that plagued conventional watches. Every detail was calculated and tested. Harrison understood that precision required eliminating every source of error, no matter how small. In November 1761, William Harrison, then in his late 20s, departed Portsmouth for Jamaica aboard HMS Deptford, carrying H4. John Harrison was nearly 70 and too frail to make the voyage himself, so he entrusted his life's work to his son. The voyage lasted 81 days, crossing the Atlantic through storms and calm seas, heat and cold, every condition that could test a timekeeper. When they reached Jamaica, William compared H4's time with the local observations. The watch had lost only 5 seconds, an error so small it translated to roughly 1 nautical mile of longitude. The Board of Longitude demanded a second trial to confirm the result, but Harrison was elated. H4 had performed beyond even his expectations. The second voyage, to Barbados in 1763, confirmed H4's extraordinary accuracy. Over a 47-day voyage, the watch lost only 39 seconds, well within the requirements for the full prize. William Harrison presented the results to the Board of Longitude, expecting immediate recognition and the £20,000 reward. Instead, the board hesitated. They demanded that Harrison reveal the watch's construction in complete detail, produce drawings of every component, and allow other watchmakers to replicate it. Only then, they said, would they consider awarding the prize. Harrison, stunned and furious, realized that the board did not want to admit that a self-taught carpenter had solved a problem the greatest scientists in Europe could not. The board's reluctance was driven by Nevil Maskelyne, the newly appointed Astronomer Royal and a powerful member of the Board of Longitude. Maskelyne was a brilliant astronomer who had spent years perfecting the lunar distance method for determining longitude, a complex technique that required precise observations of the moon's position relative to stars, followed by hours of calculation. Maskelyne had published tables and instructions to make the method practical, and he believed it was the proper solution to the longitude problem. Harrison's mechanical approach threatened to render Maskelyne's work obsolete. A watch that any sailor could use was simpler, faster, and more reliable than astronomical observations that required skill, clear skies, and laborious mathematics. Maskelyne took possession of H4 for testing at the Royal Observatory in Greenwich, and his report was scathing. He claimed the watch was unreliable, its performance inconsistent, and its accuracy dependent on constant adjustments. Maskelyne refused to apply the standard corrections that all clocks required, corrections for the known rate of gain or loss that could be factored into calculations. Instead, he insisted that H4 must keep perfect time without correction, a standard no clock of the era could meet. Harrison accused Maskelyne of deliberately sabotaging the tests. exposing the watch to unfair conditions and reporting results dishonestly. The controversy escalated into a bitter public dispute that lasted years. Parliament, pressured by the Board of Longitude, passed a new act in 1765 granting Harrison £10,000, half the prize, but withholding the remainder until he met a series of conditions. He had to reveal every detail of H4's construction, produce complete drawings, explain every component to a committee of watchmakers, and wait for those watchmakers to manufacture similarly accurate watches. Harrison, now in his 70s, was forced to dismantle his masterpiece and document its secrets. He complied, but the process was humiliating. The board also required him to surrender H4 permanently, preventing him from making further improvements or building additional timekeepers. It was a systematic effort to deny him recognition. Harrison spent the next several years appealing to the board, publishing pamphlets defending his work, and lobbying Parliament for justice. In 1772, at age 79, he made a desperate appeal directly to King George III. Harrison traveled to the royal residence at Windsor and demonstrated a fifth timekeeper, H5, which he had built despite the board's restrictions. The king, fascinated by clocks and skilled in their use, tested H5 personally and was astounded by its accuracy. George III intervened on Harrison's behalf, reportedly telling him, "By God, Harrison, I will see you righted." The king pressured Parliament to award Harrison the remaining prize money, and in 1773, Parliament granted him an additional payment. Harrison received a total of approximately £23,065 over his lifetime, slightly more than the original prize amount when accounting for interim payments. But the victory was hollow. He never received the formal acknowledgement from the board of Longitude that he had won the prize. They continued to insist that his solution was incomplete, that other methods were equally valid, and that the lunar distance method remained the preferred approach. Harrison's health declined, and he died on March 24, 1776, his 83rd birthday, bitter and exhausted. He had spent over 40 years solving the longitude problem, and the scientific establishment had fought him every step of the way. History vindicated Harrison. A copy of H4, built by watchmaker Larkham Kendall and known as K1, accompanied Captain James Cook on his second voyage to the Pacific from 1772 to 1775. Cook used K1 to navigate uncharted waters with unprecedented accuracy, writing in his journal, "I must here take notice that our longitude can never be erroneous while we have so good a guide as Mr. Kendall's watch." Cook's endorsement proved that marine chronometers were practical for exploration and navigation. Other watchmakers began producing chronometers based on Harrison's principles, and by the early 19th century, chronometers were standard equipment on naval and merchant ships worldwide. The marine chronometer transformed navigation. Before Harrison, ships navigated by dead reckoning and guesswork, accumulating errors that led to disaster. After Harrison, ships could determine their position with precision, opening the oceans to safe, reliable travel. The chronometer enabled the age of exploration, allowing Cook to chart the Pacific, Vancouver to map the northwest coast of North America, and countless others to venture into uncharted waters with confidence. It revolutionized trade, reducing shipping times and losses. It saved countless lives by preventing shipwrecks. Harrison's invention became as essential to seafaring as the compass or the sextant. Harrison's story is a reminder that innovation often meets resistance, especially when it challenges established authority. The Royal Society and the Board of Longitude were dominated by astronomers and mathematicians who believed that the solution to the longitude problem must come from astronomy, not from a craftsman working with gears and springs. Harrison's success threatened their worldview. A self-taught carpenter with no university education had outperformed the greatest scientific minds of the age, and they could not accept it. They demanded more tests, imposed arbitrary standards, and withheld recognition for decades. Harrison's persistence, his refusal to be silenced or discouraged, ultimately forced them to acknowledge the truth. Harrison's achievements extended beyond the chronometer. His grasshopper escapement, temperature compensation methods, and friction-reducing bearings influenced clock and watch design for generations. His bimetallic strip became a standard component in thermostats and other temperature-sensing devices. His cage roller bearings anticipated developments in mechanical engineering that would not become widespread until the Industrial Revolution. Harrison was not just a clockmaker, he was an engineer and inventor whose innovations transcended horology. His approach, testing every component, measuring every variable, and refining designs through iteration, became the foundation of precision engineering. Harrison's H1, H2, H3, and H4 are now displayed at the Royal Observatory in Greenwich, alongside K1 and other historic timekeepers. They are recognized as some of the most important scientific instruments ever made, masterpieces of mechanical engineering that solved one of the great problems of their age. Visitors can see the intricate mechanisms, the grasshopper escapements, the bimetallic strips, and the balance wheels, each component a testament to Harrison's genius. The clocks still function, ticking steadily after more than 2 centuries, proof that Harrison's craftsmanship was as enduring as his ideas. The controversy surrounding Harrison's prize highlights a deeper issue, the conflict between practical innovation and academic authority. Harrison approached the longitude problem as an engineer, building devices that worked, testing them under real conditions, and refining them based on results. The astronomers on the board of Longitude approached it theoretically, calculating lunar tables, developing mathematical methods, and insisting on solutions grounded in established science. Both approaches had value, but the astronomers could not accept that a craftsman's practical solution might surpass their theoretical work. Their resistance delayed the adoption of chronometers and cost lives. Harrison's legacy is not measured in awards or recognition, though those eventually came. It is measured in every ship that navigated safely using a chronometer, every sailor who returned home because his captain knew where they were, every cargo that arrived on time, every voyage of exploration that succeeded. The marine chronometer was more than a scientific achievement. It was a tool that expanded human capability, allowing us to traverse the oceans with confidence. Harrison gave humanity the ability to navigate with precision, and in doing so, he connected the world. When Harrison died in 1776, obituaries praised his clocks, but said little about the man. He was private, focused on his work, and uncomfortable with public attention. He spent his life in workshops, surrounded by gears, springs, and tools, solving problems that others declared impossible. He never attended university, never held an academic position, never sought the approval of the scientific establishment. He simply built clocks that kept time better than anyone else's, and when the world's greatest scientists said it couldn't be done, he proved them wrong. That quiet defiance, that refusal to accept limitations, was his greatest achievement. The Scilly disaster of 1707 had claimed over 1,400 lives because sailors could not determine their longitude. By the time Harrison died in 1776, that problem was solved. Ships carried chronometers that kept time to within seconds over months at sea, allowing navigators to calculate their position with accuracy unimaginable to earlier generations. The disaster that had prompted the Longitude Prize would never happen again, not because of astronomical tables or mathematical formulas, but because a carpenter from Yorkshire had refused to accept that a clock could not work at sea. Harrison's chronometers demonstrated a principle that transcends horology, that precision is achievable through discipline, that complexity can be mastered through patience, and that the greatest innovations often come from those willing to challenge authority. The scientists who dismissed Harrison's approach believed that only they could solve the longitude problem, that it required advanced mathematics and astronomical knowledge beyond the reach of a craftsman. Harrison proved that engineering, careful observation, and relentless testing could accomplish what theory alone could not. His clocks worked because he understood materials, friction, temperature, and motion, not because he could solve differential equations. The marine chronometer remained essential to navigation until the late 20th century, when satellite-based GPS systems finally replaced it. For over 200 years, every ship that ventured beyond sight of land carried a chronometer, maintaining the tradition Harrison had started. Even today, naval vessels and some merchant ships carry chronometers as backup, a testament to their reliability. Harrison's H4, built in 1759, could still navigate a ship across the ocean if needed. The technology he pioneered endured longer than almost any other invention of the 18th century. Harrison's struggle for recognition resonates because it is universal. Innovators throughout history have faced skepticism, resistance, and outright hostility from established authorities. Watt's radar was dismissed as impractical until it saved Britain. Mitchell's Spitfire was ridiculed until it dominated the skies. Brunel's ships and bridges were called extravagant until they redefined engineering, and Harrison's chronometer was rejected by scientists who preferred their own methods, even when those methods were slower, more complex, and less reliable. The pattern repeats: vision challenges, convention resists, and eventually, reality prevails. John Harrison spent 43 years building 5 timekeepers, each an improvement over the last, each pushing the boundaries of what clockmaking could achieve. He worked through illness, poverty, and endless criticism. He mortgaged his reputation, sacrificed his health, and exhausted himself in pursuit of a solution he knew was possible. When the board of Longitude refused to recognize his success, he appealed to the king. When they demanded he reveal his secrets, he complied. When they withheld his prize, he persisted. He never stopped fighting for recognition, not because he craved fame, but because he knew his work was correct and the world needed it. The scientists dismissed his clock. They insisted on astronomical solutions, on lunar tables, and complex calculations. They believed that only educated men trained in mathematics and astronomy could solve the longitude problem. A self-taught carpenter from Yorkshire was beneath their notice, but Harrison's clock worked. It kept time at sea through storms, heat, cold, and motion. It required no clear skies, no mathematical skill, no hours of calculation. A sailor could read the time, compare it to local noon, and calculate longitude in minutes. The scientist's contempt could not change that simple fact. Harrison's solution was better. In the end, the mystery of the oceans was solved not by the learned men of the Royal Society, but by a craftsman who understood that precision comes from eliminating error, that accuracy requires testing, and that innovation demands persistence. Harrison's grasshopper escapement eliminated friction. His bimetallic strips compensated for temperature. His balance wheels resisted motion. He identified every source of error and engineered it away, one component at a time. The result was a timekeeper that performed flawlessly, a device that transformed navigation and saved countless lives. The scientists scorned his clock, but the oceans proved them wrong.